Today we shall learn about Jacobi's algorithm to compute all eigenvalues of a real symmetric matrix. Before we start the discussion, we have to remember one important result about real symmetric matrices. The spectral decomposition of real symmetric matrices says that if A is real symmetric, all its entries are real and it is symmetric, then we can factorize it as P times D times P transpose, where P is an orthogonal matrix, D is a diagonal matrix, so P transpose is the transpose of this orthogonal matrix, hence it is also the inverse of this matrix. Now the diagonal entries of this D, they are the eigenvalues of A. So if I consider these as a diagonal matrix with entries lambda 1 to lambda n, then these lambda i's are the eigenvalues of the matrix A. So this led Jacobi to try to think of a method to compute the eigenvalues lambda i's in this way. He just took this P on this side and this P transpose on that side to give A pre-multiplied with P transpose. When you bring P on this side, it becomes P inverse, so that is same as P transpose. Similarly, when you take the P transpose on that side, it becomes P, and that is a diagonal matrix. Once you arrive at a diagonal matrix, you can just look up the eigenvalues as the diagonal entries of the matrix. Now the problem is, how do you guess such a P? And by the way, I should remind you that all these lambda i's must be real numbers, because there is a result which says for a real symmetric matrix, the eigenvalues are all real numbers. Let's start with the simplest possible case, 2 by 2 matrices. Orthogonal matrices as linear transformations represent either rotation or reflection, or maybe a combination of both. Now when you work with 2 by 2 matrices, then rotation matrices have a very simple form. We can write them as cos theta sin theta minus sin theta cos theta. You take any angle theta, then this particular matrix will give you rotation by angle theta. So if you rotate it by angle theta in the counterclockwise direction, then it will be, I did not say the right thing here. I want to say this is not the right thing. So if I have to rotate it like this, that is, you have to rotate it by theta in the clockwise direction. How did I understand that? Because if I consider the first basis vector E1, then E1 comes here, so you can see that its x coordinate is positive and y coordinate is negative, and that is the first column here. In this case, this E2 will now become this, which has both first and second coordinate positive, and the second column is like this. So this is the general form of 2 by 2 orthogonal matrix representing rotation. So the natural thing to try is whether we can find one such matrix P such that P transpose AP will be diagonal. There is no guarantee, of course, that we are going to succeed. Maybe we need some reflection somewhere, whether we can achieve this diagonalization merely using rotation matrices, that's not a priori clear, but we can at least try. We are looking for a solution to this equation. Let me explain. This is our 2 by 2 matrix A. Since it is 2 by 2, I can write it in this way, symmetric, so I have used same Q, otherwise PQR may be just any real numbers. Instead of writing cos theta, I have written C, and sin theta is represented by A, so that is what I call P transpose. So my P will be just its transpose, that is P. So I am trying to find out a suitable theta such that this will be a diagonal matrix. I do not care what these two entries are. They are of course my eigenvalues, but for the time being I am trying to see whether I can diagonalize A using only rotation. So what I will do is I will find out this particular entry in terms of C, S, P, Q, R, equate that to 0, and a little bit of algebraic manipulation, pretty simple, will give rise to this Cs divided by C square minus S square, that will be Q divided by P minus R. Remember, this is cos theta, this is sin theta, so the moment you look at this, you understand it is cos 2 theta. And this is pretty much close to sin 2 theta, you just need a 2 here, so supply the 2, and that gives you tan 2 theta equal to 2q by P minus R. From this you can work out a value of theta. We do not really care what theta is in terms of whether theta is this value or theta plus 2 pi, so there are infinitely many solutions. We do not really care because we care about cos theta and sin theta. So even if you take theta or theta plus 2 pi or theta plus 4 pi, all these things will give rise to the same matrix. Now you might be wondering what happens if P is equal to R, then I cannot divide. That is not really a problem because the way I arrived at this by dividing P minus R was, so originally I had this Cs times P minus R equal to Q times C square minus S square. So if P minus R is 0, then this side is simply 0, and from this you can see that if Q is not 0, Q cannot be 0 at that point. Well, Q may be 0 also, so depending on that you can solve for it. It will essentially turn out that if you interpret whenever P minus R is 0, if you consider that like infinity, then tan of pi by 2 is infinity, which is by the way not correct, but if you just use this, whatever you get will also turn out to be the answer here. I am not suggesting that you use this, but if you just follow the derivation, wherever you have P minus R equal to 0, just do that case separately and you will see that you get nice answers for theta in those cases as well. For a 2 by 2 matrix, there is essentially only one off diagonal entry. There are two off diagonal entries, but they are same. So turning that to 0 is pretty straightforward. We could do that using just a rotation matrix. However, if you have a larger matrix, then there will be many off diagonal entries and you have to make all of them equal to 0. So Jacobi suggested that you make them 0 one by one. So you start with that particular off diagonal entry which is the largest in absolute value. And then you apply this technique to reduce it to 0. Suppose this is our matrix A. In that case, we first identify which off diagonal entry has the largest absolute value, and these two are the things. So whenever this is the largest, that also has to be the largest because of symmetry. And Jacobi suggests that you focus your attention on only these 2 by 2 submatrix, these and this. So in this case, it is our row 4 and column 2. So you look at only row 2, column 4. So this particular submatrix, only this 2 by 2 thing. For this you can construct the way we did cos sine and minus sine cos. So you construct that particular matrix. So I will write it in cos sine minus sine cos. Precisely the way these things are written, you write cos here, sine here. Then you fill up the remaining things just like the identity matrix, which means you do not want to modify the others. So you write a 1 here and a 1 here, just the identity matrix, and fill everything else with zeros. So all these things are zeros. So you basically start with the identity matrix, and then in these 4 places you write CS minus SC, where C is cos theta and S is sin theta. They are computed using this formula. Tan 2 theta is this. You interpret this as P, this is R, and these two are Q's. So you pre-multiply by this matrix and post-multiply by its transpose. That will naturally reduce this and these to zeros. That is precisely how we computed C and S. Of course, some of the other entries will also change, and you can guess that this will change, this will change, this will become 0, and in the process these numbers will also change. All the things in rows 2 and 4 and the things in columns 2 and 4. All these things will change. However, everything else will remain unaffected. So all the things in rows and columns 2 and 4 will change. These off diagonals will become 0 and the other entries will remain untouched. At this point, Jacobi made a rather strange suggestion. He said that you first make the off diagonal entry with the largest absolute value 0. As a result, the matrix changes, and then you look for the largest absolute off diagonal entry in the resulting matrix and try to make that 0. Again, by pre and post multiplying by suitable rotation matrices. And you keep on doing this. Then eventually you will approach a diagonal matrix. Now on the face of it, this does not look quite reasonable, because it is just like trying to solve a Rubik's cube by taking each of the small cubes to the right place sequentially. The problem is, once you have taken one particular cubicle to its proper place, and then you are taking the second cubicle to its proper place, that might disrupt whatever you have done for the first cubicle. So when you take the second cubicle to the proper place, the first cubicle may get displaced from its place. Similarly, when you make one particular off diagonal entry 0, that's fine, but when you try to make another off diagonal entry 0, the original off diagonal entry may become non-zero back again. So it is not at all clear why this should converge. You might go round and round in a loop. But an interesting fact is that it will not happen. If at every step you try to work with that particular off diagonal entry which has the largest absolute value. In that case, all the things will eventually go towards 0, that is all the off diagonal entries, and you will indeed approach a diagonal matrix. The proof of this fact is not very easy, and we shall take up the proof in the next video. But for the time being, let's take an example and see how we might implement it in a language like R. Okay, so we will write a function. We already have a function to implement this Jacobi algorithm, one step of the Jacobi algorithm rather. So it's a function Jacobi equal to function, and A is the input matrix. It's a good idea to first write down the main steps. So the first step here is this comment: find the maximum absolute off diagonal entry. After we find it out, we compute theta based on that, and then we create the rotation matrix, the Gibbons matrix, and finally we do the transformation. So these are the basic things. Now let's go back to the first step, computing the maximum absolute off diagonal entry. Now R has various ways to find the maximum and the position of the maximum in a list. However, here we will be working with only the off diagonal entries in a matrix, and our aim is not just to find the maximum but also the position of the maximum, the I and j at which that maximum occurs. So we have to fall back on the usual nested loop solution for finding out this position of maximum. So first we take n equal to n row of A excuse me, and then I initialize the current maximum is the first off diagonal entry A21, absolute value of that, and its position is 2 and 1. This is the position of the maximum observed so far. We are just starting, so 2 1th element. Now I run the loop for I from 2 to n and j from 1 to I minus 1. Notice I am not starting I from 1 to n, because if I is 1, then there is no off diagonal entry there. And j will run from I to 1 to I minus 1. So I am looking for the maximum in the strict lower half. And if the current maximum happens to be smaller than this absolute value, then we will update our maximum. The position of the row of the maximizer will be stored in mi, the column will be stored in mj, and the maximum value so far itself will be stored in mx, and we just run the loop, and when we come out of the loop, mx should store the maximum value. Since we need to use this in order to check whether we have run enough iterations or not, so I am printing it cat mx with a new line. So that is the computation of the maximum. Now we compute theta. So the minimum occurs at mi row and mj column. So I basically use this formula, tan inverse twice the off diagonal entry mi mj and divided by a mj mj minus a mi mi. Tan inverse of that will be twice theta. So I divide by 2 to get theta. Now I am not using the usual tan inverse function a tan. I am using the function a tan 2, which basically takes care of the denominator being 0. So if the denominator ever vanishes, it still will give you the right result. A tan will not be able to handle that because it takes only one argument, and if I pass the argument like this, in that case the moment this denominator becomes 0, this will become infinity and there will be problems. So a tan 2 instead will take the numerator and the denominator as separate parameters, separate arguments, and will give the correct result. So I have theta. So I now construct the Gibbons rotation matrix. For this I need sine and cosine, and I start with the identity matrix. Diag n creates n by n identity matrix. Then I look at the mi mj cross mi mj, this 2 by 2 submatrix, and put my Gibbons matrix there, cos sine minus sine cos. And then finally I do the transformation. That's it. So this is how I write this function. Now let's put it to test. So I will load it. I have loaded it. Now let me create. Let me increase the font size a bit. Yes. So I will create a symmetric matrix. How do I create a symmetric matrix? Well, I will first just create some matrix. So I will take, say, random normal number maybe. And how many? 25 suppose. And I will wrap it into a matrix, 5 by 5 matrix, 5 by 5. So that gives me a matrix, of course, not symmetric. In order to turn it into a symmetric matrix, what I will do is I will create the matrix B, A plus transpose of A. This matrix is bound to be symmetric, and indeed it is symmetric. So let's now try to apply our Jacobi function. So Jacobi of B. That gives us a new matrix, and it also prints what is the maximum off diagonal, absolute off diagonal entry it has encountered. Of course, just by running it once, we will not be able to understand anything. So what I will do is, I will start with, so I will store B old B, so that if I later need to work with it, I will be able to use it. And now I will write for I in 1 to how many steps? Suppose I do 100 steps. So ideally I should do a check about how many steps I should do, but right now I am just being lazy. I am going to do this. So I am going to apply the Jacobi iteration 100 times. At every step it is going to print the maximum off diagonal entry, the maximum absolute off diagonal entry, and here we see it is 10 to the power minus 146, pretty close to 0. So it is very, very close to diagonal. Excuse me. So let's take a look at our B. After all this transformation, you will notice that all these off diagonal entries are effectively zeros, and these are the eigenvalues. Therefore, this is one eigenvalue, 3.249, etc. This one is 1.77. This one is minus 1.06. Oh, there is a 10 to the power minus 1. So it is minus 0.106. This is minus 2.86. This is minus 4 point, etc. So this is what we get. Now, how do I know that this is correct? That's why I stored that B old. I will use directly the eigenfunction of R to check that what I got is correct. So these are the eigenvalues reported by R. 3.24, etc. Yes, pretty close. 1.77, yep. Minus 1.06, minus 0.106. Yes, we have a 10 to the power minus 1 here. Minus 2.8 and minus 4. So it is indeed pretty close to the eigenvalues as reported by R. Okay. So that's essentially what I wanted to discuss.